Hello guys, so this is basically the second recording of week one. I'm gonna use here slides from Dr. Vincent. It's our colleague here in the department. It's really very good slides. So I just discard mine and use them. So we're gonna discuss now about numbering and number systems because we're gonna deal with the computer or processor, and the processor will do some computation for us. And for that reason, we need to understand what kind of numbers the processor can handle. Can it handle, the normal numbers that we see every day? 1, 2, 3, 4. Can he do that? Let's check. So the numbers that we are used to see every day is called decimal numbers. And sometimes they call it base 10 numbers. And base 10 because you have 10 digits or 10 different shapes or figures that, constitute any number in this system. Okay, basically the numbers from 0 up to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. From these 10 different shapes, that's why they call it base 10. Okay, you can construct any number. Okay, and here are examples, of course, for such as you see here, you can see the digits from 0 up to 9. That's why they call it base 10. Can we do another number systems, like a system that has, for example, just two figures or two shapes or two symbols? Yes. And in that case, it will be called base 2 or binary numbers. And the binary numbers has two symbols or figures from which you can construct any number. And these two numbers are 0 and 1. It's always less than what. So if you say base 10, then you can do from 0 to 9. If you say base 2, you can do from 0 to 1. Okay, so based on the 0 and 1, just these two symbols, you can construct any number. These are examples from numbers. Of course, it's not it's difficult to understand, or not difficult to understand, difficult to recognize what kind of number is this. But we're gonna learn in a moment how to convert from binary to decimal and from decimal to binary. Because this is not, this is maybe computer readable, not human readable. But we can convert and know what kind of number is this. And why it's called binary, as I said, there are two symbols, okay, 0 and 1, and the word bi in Latin means, 2. And the basis for any, this is basically the basic idea behind the conversion, is that like what you have in the normal system or base 10 system, okay, each digit has its own weight. Exactly the same here. Each digit or each bit, because we call it bit here, has its own weight. Like let's take an example, like 980. I said 980. So, or 81, let's make it 81. So we can do or write this number in that way: 900 plus 80 plus 1. Or you can write it in that way: 9 multiplied by 100 plus 8 multiplied by 10 plus 1 multiplied by 1. And then the final step here, you can write it in that way: 9 multiplied by 10 to the power of 2 plus 8 multiplied by 10 to the power of 1 plus 1 multiplied by 10 to the power of 0, which is 1. We call this weights columns. Exactly the same here in our binary system. Like, for example, the number 1, 1. This is not 11. In binary, this will be 3. Let's check. So this is 1 multiplied by 2 to the power of 1 plus 1 multiplied by 2 to the power of 0. This is basically the conversion from binary to decimal. 1 multiplied by 2 is 2, and 1 multiplied by 1, remember this is a 1. Anything raised to the power of 0 is 1. Plus 1, it's equal to 1. So basically 2 plus 1 is 3. So this is not 11. That's why we discriminate between them by putting this, subscript 2. And here are some more examples, like 0 in decimal is 0 in binary, no problem. 1 in decimal is 1 in binary. But now start the, the tricky part. 2 in decimal is 1, 0. This is not 10. That's why we should name the column here as binary. So we don't need to put the parentheses and the base 2 stuff. 3 is 1, 1. This is again not 11. 4 is 100 or 100, not 100, and so on. So this slide is talking about the discrimination that I said. As I said, you can have one number. This number can be read, in 2 different ways with 2 different meanings in binary and decimal, like 101 or 101. This is in decimal is 101. But in binary, 101, you should convert it. So 1 multiplied by 2 to the power of 2 plus 1 multiplied by 2 to the power of 1 plus 1 multiplied by 2 to the power of 0. I'm sorry, this is 0. So this will be 2. I'm sorry, this will be 4 because 2 to the power of 2 is 4 plus 0 plus 1. This is 5. Okay, guys. Now, how to convert from binary to decimal and the opposite as well. Also, although we have talked about and see examples, but we're gonna take it in a more formal way and with more details. Let's first talk about converting from binary to decimal. I already did this. So basically you write down the columns and you multiply then add. Like for example, the 101 example. So this is the number that we want to convert, 101. And here are the columns or position values or the weights. Call it whatever you like. And always start from the least significant bit. Least significant bit or digit. In binary, we usually call it bit, but you can call it digit. To the most significant bit. Put the weights, then multiply, then add. Let's do it without looking at the slide. So 101, start by the least significant bit. This is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. Then multiply 1 multiplied by 1, 2 to the power of 0 is 1. Will give you 1. 0 multiplied by 2 to the power of 1 is 0. 1 multiplied by 2 to the power of 2, which is 4. This will give us 4. Add these together. This will be 5. Very easy. Here is the idea of the columns again. He is just stressing on that idea. Let's take another example, like this number here. So 1 is corresponding to 1, or 2 to the power of 0. 0 here is corresponding to 2 to the power of 1. This 0 or this bit is corresponding to 2 to the power of 2, which is 4. This one is corresponding to 2 to the power of 3, which is 8, until you reach here the number 7, because you start from 0 until number 7 here. So this is 2 to the power of 7, which is 128. And exactly the same stuff. You multiply, then at the end you add these together. This will give you 105. Let's take another example. This number here. Again, same stuff. 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, until 2 to the power of 7. You multiply, then you add. This will give you 156. Some terminology here. The digits inside the binary number is called bits. Okay. And when you have 8 bits together, we call it byte. We're gonna use the word byte, all over the place, in our next lectures, because it can be a unit of measurement, or measurement the size of a memory, for example, in your computer. Also, another definition is how many, or another question that you should answer here is how many different numbers you have from how many bits. If you have 2 bits, how many different number we can represent? If you have 3 bits, how many numbers we can represent with 3 bits, and so on. So if you have 2, it's always 2 to the power of how many bits you have. So if you have 2, then 2 to the power of 2 will give you 4, which is basically 0, 0, 0, 1, 1, 0, 1, 1. If you have 3 bits, then the number of combinations will be 2 to the power of 3, which is 8. Let's do it. So I'm going to give you a very good way to do it. You start by 0, you have 8. So start by the most significant bit here. Okay. Then you write 4 zeros, then 4 ones. Then go to the next bit. 2 zeros, 2 ones, 2 zeros, 2 ones. Then the last one will be alternating all the time, switching all the time. 0, 1, 0, 1, 0, 1, 0, 1. So you start from 3 zeros, you end up with 3 ones. You must end up with 3 ones. If you do something else, you have a mistake. And these are 8 combinations. 1, 2, 3, 4, 5, 6, 7, 8. This is the same here. And this is the general rule. If you have n bits, then you have 2 to the power of n different binary numbers. Smallest value for any binary number is always 0. It's always 0. That's why we start all the time from 0. Look, we started here from 3 zeros. We started here from 2 zeros. The largest value of any binary number, it's always all the time, you know, just ones, both ones, okay? And a very good rule here to convert this number, if you have, for example, 3 ones, these are 3, right? So to read it in decimal, we should convert. So this will be 1 multiplied by 2 to the power of 3 plus 1 multiplied by 2 to the power, 2, 1, then 0. It will give you 7, right? These are 3 bits. 2 to the power of 3 is 8. So look at the relation here. So it's always 2 to the power of n minus 1. So this is a good way to convert without a conversion. You know, just in your mind, you have 3 bits. 2 to the power of 3 is 8, minus 1 will give you 7. So 1, 1, 1 will give you 7. Here are some other examples. Now, how to convert a decimal to a binary, which is more important because our computer, our processor, doesn't understand what we see, you know, the decimal numbers that we see 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. No, it doesn't understand this. It's an electrical machine. So electricity, it understands the world from this view, you know, view or angle. Like there is electricity, there is voltage, there is a charge, and absence of a charge. Absence of voltage, or voltage is equal to 0, or low voltage, high and low, 0 and 1. There is electricity, there is no electricity. That's the basic, you know, understanding of a computer. So the processor must be fed with zeros and ones. So our numbers, which is base 10 from 0 to 9, should be converted to binary, because binary is a very, you know, close system to what the computer understands. 1 means there is a charge, there is electricity. 0 means there is no charge, there is no electricity. So it can understand the world from that way with a base 2 numbers. So we need all the time to convert what we understand to what the computer understands, to what the processor understands, and in our course, what Intel architectures understand. Okay? So we need to know or to find a way to convert from, translate from our language to the computer language, or to convert from decimal to binary. Okay? So we're gonna take two ways here. I'm gonna skip the explanation to directly to the, you know, examples. Yeah, here is one example. You want to convert 106. So what you're gonna do is you write down the weights, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, you know, until you reach a weight which is greater than the numbers that you want to convert. Okay, so let's do that. I'm gonna append to, so this is 2 to the power of 0, which is 1, 2 to the power of 1, 2 to the power of 2, which is 4, 2 to the power of 3, 8, we still less than 106, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, which is 64, still less than 106, 2 to the power of 7, it's 128. This is greater than 106. So we're gonna exclude it. That's the way. You start writing the weights or the column values until you reach a weight greater than the numbers that you want to convert. So we exclude this one. So the weight from 2 to the power of 0 until 2 to the power of 6, which is 64, is enough for us. Then you compare each weight to the numbers that you want to convert. If it's less than, you put 1. If the weight is less than the numbers that you want to convert, you put 1. If it's greater, you put 0. Once you do that, you subtract. If you put 1, I mean, if it was less than the number, you put 1, then you subtract and convert the subtraction in the same way. So let's do that. 106. 64 is less than 106. So 64 here is less than 106. That's why we're going to put 1 here. Of course, Dr. Vincent did that in multiple slides, but we're going to do it in one slide now. Okay. Since we put 1, then we take 106 and subtract, 64 from it, and it will give us 42. 42 is less than, is greater than 30, is 32. So 32 is less than 42. So you put 1. That's good. Then you subtract 42 minus 32. It's 10. Oh, 10 now is less than 16. So 16 here is greater than 10. That's why we're going to put 0 here. Good. And the continue comparison. So 8 is less than 10. So you're going to put 1 and subtract. So 10 minus 8 is 2. 2 is less than 4. So we're going to put 0 here. So 4 here is greater than 2. But 2 is equal to 2. That's good. That's fine. So 2 is equal to 2. So you're gonna put 1 if it's less than or equal. Then you subtract 2 minus 2 is 0. 1 is greater than 0, so you put 0 here. And that's the number. That's the conversion here. Let's put a rectangle around it. How to check on that? We have 2 ways, a hardware and a very simple way. The hard way is to convert it back. Let's do that. So this is a number 1 1 0 1 0 1 0. Just to convert it back. So what you're gonna do is to multiply, each digit or each bit by its weight, and you have the weights already here. So 1 will be multiplied by 2 to the power of 6, 64, plus 32, plus 0, plus 8, plus 0 again, plus 2, plus 0. So let's do that. You have here 90, so these 2 will be 96. 8 plus 2, so 98 plus 8, it's 106. So it's correct. This is the hard way. The easy way, and the good news as well, is that you can do that on your calculator or online. Okay, you can just write on Google, 106 to binary, and it will give you the conversion directly. It's really simple. Okay. Now this is how to do it. This is basically how Google do it. So there is a calculator somehow that Google will use, and the algorithm inside of the calculator will do that stuff. Okay. So basically the rest is just the rest of the example. We already did it. The second way of the conversion is, which is maybe easier, I don't know, It's based on the preference, personal preference is by division. We're gonna check, take an example and check how to do that. So let's take our first example here. So 189. What you're gonna do is you divide by 2 and record the remainder of this operation until you reach 1. Then you cannot divide further. So 189 divided by 2 will give you 94, and the remainder is 1. And this one here will be part of the final conversion, and it will be actually the least significant bit, least significant bit, LSB. Then you take the 94 and divide by 2 will give you 47, and the remainder is 0. 47 divided by 2 will give you 23, and the remainder will be 1. 23 divided by 2 will give you 11, and the remainder is 1, because 2 multiplied by 11 is 22. Just 1 away from 23. So the remainder is 1. Then 11 divided by 2 will give you 5. The remainder is 1. Again, 2 multiplied by 5 will give you 10. 1 away from 11. So the remainder is 1. 5 divided by 2 will give you 2, and the remainder is 1. 2 divided by 2 will give you 1, and the remainder is 0. We take the 1 and divide by 2. 1 divided by 2, it's greater. It's not greater and not equal. It's less than 2 basically. So the result is 0, and the whole number, which is 1, is a remainder. And actually, this is again part of the final conversion, but it will be the most significant bit. Most significant bit. And it's really important to know which is the least and which is the most significant bit. Very important. So we're gonna write it in that way. So this is the 1 here. This is the most significant. Then the 0. Then the 4 ones. Then the 0 again. Then the 1. Maybe here, because the number is symmetric, you don't care which is most and which, but for other examples that we're gonna see in a moment, example 2 and 3, it's really important. Here is our second example, 75. And here are the, the steps one by one until you reach the final, and you cannot divide further. Okay, 75 by 2, or I'm sorry, divided by 2 will give you 37, and the remainder is 1. 37 divided by, and this will be the least significant bit. 37 divided by 2 will give you 18, and the remainder is 1. 18 divided by 2 will give you 9, and the remainder is 0, until you reach, 2 divided by 2 will give you 1, and the remainder is 0. And then the 1 divided by 2 will give you 0, and the remainder of 1. And you cannot divide further. You cannot go further here. Why? Because if you do, it will result in nothing. Let's check. If you want to divide further, we're going to take the 0 and divide it by 2. 0 divided by 2 will give you 0, remainder 0. Then you're going to have an infinite loop of, of unchanged stuff. So 0 again divided by 2 will give you 0, remainder 0. And if you're going to continue in that way, you will not finish. That's why we stop at that point. And this will be our most significant bit. The one on the further left. And that will be our most significant bit. Then the 0 will follow. 2 0 0, 2 0 0. Then this one here. Then 0, then 2 1s. And if you want to check on yourself, just to convert this back to decimal. the final example. It will convert to 242. Here are the steps again in animation. So 242 divided by 2 will give you 121, 121, and the remainder will be 0. This will be our least significant bit. It's always if you have an even number, the least significant bit will be 0. So all the time like this. If you have odd, it will be all the time 1. 121 divided by 2 will give you 60, and the remainder is 1. Then 60 divided by 2 will give you 30, and the remainder is 0, and so on until you reach that, final step here, when you reach a result of 1. And this will be the most significant bit. So here is the most significant bit. Then you have another 3 ones. Then you have 2 zeros. Then you have 1. Then you have the 0, which is the least significant bit. And again, to check on yourself, convert this back or do the, calculator. It will give you the same result, 242. So that's it, guys, for this part of the lecture. Thank you very much, and see you in the next recording. Bye-bye.